So, welcome everybody to this fourth in the series of coffee talks brought to you by the Global Forum for Geography and Statistics, GFGS, the European Free Trade Association, EFTA, and my organization, United Nations Economic Commission for Europe, UNECE. I'm Steve Vail. I'll be moderating this session today. So it's great to see that we have participation from right around the world, and that's really exemplified, I think, by our two presenters. So for Kevin on the west coast of the United States, it's very, very early in the morning. And for Matt in Australia, it's already pretty late in the evening. And I think for the participants, it will be somewhere in between that. So we're going to be talking today about developments in applying global grids. And as usual, we have two presentations, which will be followed by question and answer and open discussion time. I'd like to ask all participants to keep your microphones muted and preferably keep your cameras off unless you're a presenter. And also, if you have any questions as we go along, please write them in the chat. After the two presentations, I'll take the questions from the chat and put those to the presenters, and that should be the way of getting the discussion started. So I think without any further ado, we can start going to the first presentation. So Kevin Saar of the Southern Oregon University, over there on the west coast of the United States, has the presentation, So You're Thinking of Trying a Hex DGGS. So Kevin, I give the floor to you to explain what's involved with that. Thank you.
Thank you. Get my screen up here. Apologies. All right, so what I wanted to do this morning was just to give some quick advice to someone that might be trying or thinking of trying out a Hex Discrete Global Grid system. So to motivate the talk, I'm going to talk to a specific use case. The one I'm going to say actually applies to lots of different use cases, but the use case I'm going to use to motivate the talk is you've got lots of geospatially referenced point data, and you want to put it into a grid to analyze it, visualize it. Maybe you want to do some machine learning, pattern recognition, whatever it is you want to do, but you want to put it into a grid for analysis and visualization. All right, so first off, what is a discrete global grid system? Well, a discrete global grid, and here I'm just going very simple and fast, but a discrete global grid is really just a regular grid that covers the entire globe. And the idea of a discrete global grid is that it facilitates comparison between areas across the globe. So rather than having different grids in different places that don't necessarily spatially work well together, you're gonna have a grid that covers the whole surface of the globe, and then people in different areas can put data into it, and it's comparable and the same grid everywhere. And maybe you want to do multiple resolutions with your data. You want multiple resolution grids. Well, we call that a discrete global grid system. It's just multiple discrete global grids with different resolutions. Well, the first thing you're going to have to do is decide on the shape of the cells in your grid. And of course, square grid cells are by far the most common choice on the plane. And there are square-based discrete global grid systems. So for instance, our HeelPix, which Matt may be discussing a bit, and there's Google S2. Those are both square-based discrete global grid systems. But maybe you've tried hexagons on the plane, hexagon grids, or maybe you've heard about hexagon discrete global grid systems, and you're thinking, well, maybe you want to try that. Well, why might you want to try that? Let me talk a little bit to why I think hex discrete global grid systems are the superior choice. All right, so first off, recall our use case. We've got a bunch of data points. We want to bin them into the grid. So each grid cell is going to represent a set of data points. And we want those points to ideally have similar values so that the cell actually displays information rather than just sort of a gray munge of data. So we know from the first law of geography that the nearer points are together, well, the more likely they are to have similar values. So we want a compact cell that minimizes the maximum distance between any 2 points that cell represents. Well, hexagons are the most compact regular polygon that tiles the plane. And in fact, tiling the plane with hexagons rather than squares requires about 13% fewer hexagons versus the same resolution squares. So right off the bat, you get over a 10% win just on the number of cells you need. All right, so you've got the most compact cell, you've got the most efficient quantizer. Both are hexagons. Important feature of hexagons is that the neighborhood of hexagonal cells is unambiguous. So in the case of squares, we've got 2 types of neighbors. We have the edge neighbors, and then we have corner neighbors. And those neighbors, those 2 types of neighbors, are different distances from the center cell. In the case of a hexagon grid, well, we've only got 1 kind of neighbor, and they're all the same distance from the center hexagon cell. And this circularity of neighborhood extends out to n-order neighborhoods. So the second-order neighbors here, still we've got this sort of square shape, and we've got neighbors at different distances from the center. But in the case of the hexagon grid, all of the neighbors are the same distance away. And that continues out rings of hexagons. So hexagons are more circular, both in the sense of hexagons being more compact, more circle-like, and their neighborhoods being more circular, of the same radius as we go out. So hex grid distance, the metric distance on the hex grid, is a better approximation of Cartesian distance than on a square grid. So it makes a really nice surrogate for Cartesian distance, a very efficient surrogate. What also this gives us is superior angular resolution. So can we resolve more different angular relationships between the data points in our set? Okay, so all this taken together means that common image processing algorithms that are radially symmetric operate at 25% to 50% more efficient than the square version of those algorithms. So that's significant right there. Again, 2 times speed up for common image processing operations. It also means that if we display an image, if we visualize an image on a hex raster versus a square raster, it's less blocky. Everyone I've ever talked to or discussed this with feels that hexagon grids are more aesthetically pleasing to look at, and in fact are visually a more accurate representation of the underlying data. They don't look as pixelated as square grids. And because hexagons are so efficient, well, nature always chooses the maximally efficient choice, and hexagons are used throughout nature, including in the arrangement of the photoreceptors in our eyes, and in the way that our brain represents spatial relationships. It actually does it on a set of neurons that are arranged in a hexagonal grid. Okay, so we want to use a hexagonal discrete global grid system, let's say. One thing we have to note is that it is impossible to actually tile the sphere with just hexagons. You've got to have some other shape in the mix to mathematically tile the sphere. So the most common hex discrete global grid systems that are out there right now all are based on the icosahedron, and we place 12 pentagons at the 12 vertices of the icosahedron. And these 12 pentagons are there in every grid resolution. There's not more of them. They just get smaller and smaller as we go down. There's always 12 pentagons. So you have to keep that in mind. All right, so let's say we start with some base set of cells at some resolution on the globe. How do we get finer grid resolutions? Well, again, the most common approach to doing this right now, and it's certainly not the only approach, but the most common approach that you'll see out there in the wild is to use what's called an aperture. So we can create grids that have a regular relationship to our original grid that have cells that are 1/3, 1/4, or 1/7 the area of that original grid. And we refer to this as aperture 3, aperture 4, and aperture 7. So 3 different ways of getting finer resolution grids from a given grid. DGS can have the same aperture throughout the entire discrete global grid system. So we have an aperture 3, for instance, as we go down to finer and finer levels, or we can mix the apertures and have an aperture 3, an aperture 4, an aperture 7, and so on. And we achieve what we call a mixed aperture discrete global grid system. Both are possible. All right, so all these amazing things about hexagons, but of course there's always a downside to anything. So why might we not want to choose a hexagonal discrete global grid system? Well, there's two primary reasons. First, hexagons don't nest like squares do. We can't take a hexagon and break it up into smaller hexagons. We can't take a bunch of hexagons and put them together to get a bigger hexagon like we can with squares. And this is a potential problem if we've got data in a particular grid and we want to build coarser grids just using that gridded data. Okay, you can't do that. Well, let's talk about how we might want to approach that with a hexagonal grid. With a square grid, it's easy. Obviously, we can just put the squares together to create bigger squares, and now we have a coarser grid. But we can't do that with hexagons. Okay? Well, first off, let's remember the use case that we started out with. So we've got a bunch of point data. All we really need to do is to bin it into whatever grid resolutions we want. So we can bin it into multiple grid resolutions, and there isn't really any issue at that point, right? Instead of binning it into a fine resolution and attempting to build a coarser resolutions using that fine resolution, we just bin it into whatever resolutions we need the data to be in. And because the boundaries are not absolute in multiple resolution hex grids like they are in square grids, this process can actually put more information into our, what we call an image pyramid, multiple resolutions of bin data. So we can reduce certain grid artifacts that result from the absolute boundaries that occur in a square, in a hierarchical square grid. So for example, the modifiable areal unit problem, where the gridding can change as we move the grid in relationship to our data and could do things like make hotspots not visible in our data and things like that. Well, this is to some extent reduced if we use a multi-resolution hex grid, so that as we change resolutions, the grid in effect moves on its own. So it can actually be an advantage to do this. Alternatively, well, what if we say we don't have access to the data? Say all we have is the data in one particular resolution already binned. There is an approach we can take to building coarser resolution grids using that data, and it works best with Aperture 7. Actually, it really only works well with Aperture 7 discrete global grid systems. And we note that in an Aperture 7 system, we can group these fine hexagons into groups of 7 hexagons. And then these groups of 7 hexagons have a hexagonal relationship to each other. And we can group those groups of hexagons into a group of 7 groups of hexagons. And those groups of hexagons have a hexagonal relationship to each other. So these groupings are not true hexagons, they're pseudo hexagons, as it were, but they do have a hexagonal resolution. And if you're using an equal area grid, they do have equal area as we go up. So you can use this process to actually create essentially a coarser resolution grid by grouping data in a particular already binned grid resolution. And this, incidentally, is the approach that Uber takes when they work with their Aperture 7 discrete global grid system H3, which we're going to talk about in a second. Okay, so there are ways to handle the situation that hexagons don't nest. We can work around that. There's various workarounds that may even be advantageous. Second issue, well, there aren't a lot of tools right now for working with discrete global grid systems in general, not just hexagonal discrete global grid systems, but any discrete global grid system. Traditional GIS and geospatial database systems, well, for them to work with our discrete global grid cells, they just treat the cells as arbitrary polygons. So we don't really get the advantage that having grid-based data gives us in processing power because the discrete global grid systems are not built in to traditional geoprocessing systems. But I would point out that working with the discrete global grid system in a traditional GIS can still complete our use case of taking a bunch of point data and binning it into the grid and then visualizing and analyzing and so on. And this was demonstrated a couple of years ago, the Global Forum project Fairhair. And here we demonstrated, I generated a bunch of discrete global grid cells for various countries, and then we took population data and using traditional workflows, GIS workflows, bin that data into these grids and got results. So you don't really need to have a system that's tailored to working with discrete global grid systems. You could actually get away with just doing it in a traditional workflow. All right, so let's talk about again, I'm assuming you're a new user, you haven't tried Hex DGS yet. Kind of what are your choices? What can you easily get into in terms of a Hex discrete global grid system? And there's really two most widely used systems. And right now, these systems, I would estimate, account for about 90% or more of Hex discrete global grid usage. And these are Uber H3 and DG Grid, which isn't actually a discrete global grid system. It's a software for creating discrete global grid systems. And both of these systems are open source, so you can use them without paying any money. All right, so let's talk about each of these briefly. First off, the H3 Hex discrete global grid system. It's an Aperture 7 discrete global grid system, and it really is implemented in the core as an open source C library available on GitHub. And H3 was developed for a particular set of use cases for Uber, and I did participate in the development of this. It wasn't intended to be a general purpose grid, but it is being widely adopted as a general purpose grid, really because there aren't a lot of options, at least options that are so well developed as H3. It is a C library, so you can use it in C, but there are bindings for common languages like Python, JavaScript, and Java. And H3 is under active development. It is, though the grid itself is mature and isn't going to change, the software ecosystem around it is actively developed by professional software engineers. So it's a nice, solid project. The H3 DGGS provides 15 resolutions. The finest resolution is just under 1 meter squared. One thing to note about H3, the cells in H3 are not equal area. It uses a polyhedral mnemonic projection to create the cells. So over the surface of the Earth, there's a variation of about 60% in cell area. However, that wasn't a big deal to Uber because they're only worried about using the grid at city level. And at city level or small local levels, well, the variance in area is very small because it varies very gradually over the surface of the Earth. If you're working in one portion of the surface of the Earth, you don't even notice the fact that the area isn't equal. So all right. So how do we use H3? Well, again, H3 is a set of software libraries. So if you're a programmer or you have a production workflow that involves programming, say in Python or JavaScript or C, well, then H3 integrates very nicely into that. That's what it's made for. And to get you started, I would suggest just Google because there are a ton. And every week, I do the search every week, and there are more and more examples of people using H3, and people are, of course, glad to share their code and demonstrate what they've done. So go out there and look at user examples to get yourself started very quickly with H3. An alternative to using it programmatically, there is a tool being developed called Unfolded Studio. And this is Unfolded is a company that was started by ex-Uber engineers, visualization engineers, and it's a cloud-based geospatial visualization platform. And they're also spinning it as an analytical platform. There are those capabilities, but I expect those capabilities will get more and more as it goes along. Unfolded is a very new product, but it's built on technologies that have been used at Uber for a number of years. So the technologies themselves are mature and they're very state-of-the-art in terms of web-based graphics. So there is a free tier for using Unfolded Studio, and it's easy to take data files and drag and drop them into an H3 grid using Unfolded Studio. So if you want a quick way to get started with H3 and you're not a programmer, Unfolded might be your best bet. Okay, so that's the first choice. The second choice in Hex DGGS is DG Grid. And DG Grid is an open source command line C++ program, and it's meant for generating and working with discrete global grid systems. It is available on GitHub, and it was developed by me, and it continues to be developed by me and other software engineers that contribute, but it was originally developed for the United States Environmental Protection Agency. DG Grid, again, DG Grid itself is not a DGGS. DG Grid generates DGGSs, and it can generate all sorts of DGGSs, not just Hex DGGS, but triangles, quadrilaterals. But in terms of Hex DGGS, you can generate grids that are Aperture 3, Aperture 4, Aperture 7, or any sequence, mixed sequence of those apertures. DGGS provides multiple projections you can use in creating these grids, but the most common one people use is called the ICEA projection, the icosahedral Snyder equal area projection, and it is an equal area projection, which is why people choose to use it. And this allows you to get equal area cells across the globe, except for those 12 pentagons, of course, but those 12 pentagons are 5/6 the area of a hexagon. Because we can generate mixed aperture sequences with DGGrid, there's over 100 different resolution grids possible. I can't tell you exactly how many because I don't quite know how far we can go down with DGGrid. You know, I've pushed it fairly far, but there's certainly more than 100 different grid resolutions that you can generate with it. So if you're looking for a particular grid resolution to match the size of your data, then DGGrid is a good choice. So how do we use DGGrid? Well, first, it's meant to be built and run from the command line. It is a power tool, and it was written by, well, me, a programmer. And so there is a bit of a steep learning curve. If you're not a programmer, you don't have a programming background, or even if you do and you're new to DGGrid, it does take some time to get up to speed with it and get it working. So it is most commonly at this point used via a wrapper for R, for the R statistics package called DGGrid R. And this was developed by a gentleman by the name of Richard Barnes. And this allows you to access the DGGrid functionality from within R. And that is also available on GitHub. So that's one way of going about that. So because it is so hard to work with DGGrid, and I do want to encourage people to get started playing around with these grids, I decided to make a little offer here. So if you're a participant here and you want to experiment with a Hex discrete global grid system without having to deal with DGGrid, here's the offer. I'm going to choose 5 randomly selected participants who send me an email, and I will generate an ICEA grid for you. And I'll generate it as at whatever target resolution you want and at coarser resolution, so you can experiment with multiple resolutions. And I'll give it to you as a shapefile, so you can then take it and use it in your workflow as if it's just arbitrary polygons. And I'll do about 5 of those. Really depends how many people want to try this and how long it takes. Okay. And all I'm going to ask in return is that you prepare a single slide, or possibly more slides if you want, but a single slide of what your experience was working with the discrete global grid system cells and present it at a future coffee talk. So the details on the offer to participate, email me, sarek@sou.edu, and just tell me what your desired study area is, the approximate finest desired cell area, and a brief description of what you were going to try to do with the grid. And this is just so I can know that you actually are going to do something, that you actually have sort of a plan. And so email me before 1 week from today, so Thursday, May 6th, I'm going to choose 5, let's say 5 to 10 of the emails I've gotten randomly, and those people I'll generate grids for. Okay, and that's all I've got.
Great. Thanks for that, Kevin, and thanks for that very generous offer. I put a copy of Kevin's offer in the chat, so if you need to get his email address and the details and so on, grab that from the chat. And of course, we'll also put all of the slides on the GFGS wiki site as well. They'll be up there certainly an hour or 2 after this webinar. So, great offer there from Kevin. It'd be interesting to see how many people can
Alrighty. Can everyone see my screen?
Oh, sorry, I just realized I was talking on mute for a while then. Was that all on mute?
Fair bit. Not all of it, I don't think.
No, not all. Just the first part, the last part.
Okay. So yeah, just to repeat then, Kevin's offer is in the chat, and it'll be great to see how many people take him up on that. And we'd also like to see the results here at one of these Coffee Talk webinars. So now we go to the second presentation, and I see it's already up on the screen. This presentation is from Matt Peirce, and this is in Matt's role as co-chair of the Open Geospatial Consortium's working groups on discrete global grid system domain and standards. So Matt's going to tell us about the work that's been done within the Open Geospatial Community Consortium on developing APIs for discrete global grid systems. So over to you, Matt.
Beauty. Okay, thanks everyone for dialing in at varying times throughout the day. So my talk's going to be a lot more higher level than Kevin's, focusing on one of the real challenges we have of we've got all of these different varieties of DGS out there, and they've got different pros and cons and properties and characteristics. But at the moment, driving interoperability between those DGS instances and externally, as Kevin pointed out, it can be a bit tricky to do that crosswalk into and out of the DGS realm. That's a significant challenge that we have, and so my talk will be about where the OGC APIs come into this and where we're heading in that framing the context of DGS. Okay, so yes, as a bit of an overview, I'll give a very brief intro to OGC APIs, and then I'll go into giving a bit of a cook's tour of some recent implementation projects exploring DGS APIs or possibilities of how that might work, and then we'll finish with a sort of, well, really it's a statement where within the OGC we are already working towards drafting an OGC API specification for DGS, and so we're in the requirements gathering sort of phase of that right at the moment. Okay, so I did include a video, a promotional video that the OGC have put together, dealing with the whole sort of plethora of OGC APIs that are out, and the whole concept. Unfortunately, the sound doesn't sort of travel through from my computer through to everybody else. So what I've done is I've got the that's the link up on the screen there. Another alternative, I really suggest that you go and have a look at it. It's a really it's good. It's high level, but it gives you a really good understanding of what OGC APIs are about and where the OGC is trying to head with them. So yeah, the link's up there on the screen. Alternatively, if you sort of went to the OGC homepage and search for OGC APIs, then you would sort of see a link for this video pretty much straight away. So the way the OGC APIs is structured is a little bit different to web services, which were these big monolithic sort of things that just sort of pumped data out to the masses. OGC APIs following the Open API sort of concept of, I guess, decentralized sort of resource sharing, and so it's all about sort of these modular resources that are able to connect to each other via standardized sort of terminology pathways. Now, fundamentally, one of the failings of the sort of, I guess, the standards sort of challenge of web services was there were a whole bunch of common features, but they just kept getting replicated in different web service standards, and so you just get this sort of bloating. They've made in creating or sort of migrating or moving towards OGC APIs, one of the very clear and conscious things that has been done, not only by the sort of OGC sort of secretariat, but also the OGC participants, is to really enshrine the use and reuse of common sort of features. And so yeah, and so we have a sort of set of specifications of OGC API for common. So all OGC APIs must adhere to at least the core part 1, but depending on sort of what they're doing, sort of some of the other parts as well. But it means that this becomes a central sort of hub, and then other things just sort of draw and add on from that. And as you can see, there's a link there to the draft specification for those who want to dive in and have a look at the details of that. And one of the, I guess, the key things I want to point out here is sort of in the core common sort of APIs really revolve around 3 things: a landing page, so where you get to that resource, a conformance page which defines, well, which OGC standards and classes does this server or service conform to, and then an open API style of description that describes what this what this server sort of does, or what this sort of service or resource does. And that's pretty much it in a nutshell. The OGC API so common has been extended to sort of multiple parts, and so there is a geospatial data extension to this, which is trying to deal with some of the more specific but still common features that deal with geospatial data. Things like collections. What does a collection mean? Is it an item? Is it a coverage? Is it a set of tiles? Is it even a DGGS? So these are sort of, I guess, the way that the sort of the building blocks and the complexity of the data that we deal with can be sort of incrementally built upon this common backbone. This allows for sort of, I guess, linking and lists and sort of expansion of this, but it's all being driven through a common sort of schema language, being a JSON encoding often, and a consistent sort of set of protocols and descriptions. All right, and then that brings us to this question of, well, what can a DGS API share with any other OGC? So for those not familiar, API stands for Application Programming Interface. It really it's the front door to a resource. And so if it's, whether that's a DGS or something else, then that's pretty much it. So one of the things that the OGC APIs sort of provides is it provides an opportunity for different DGGS backends to live on the server, but to be accessible via a DGGS agnostic API, where the user or the front door is really asking the spatial question you want to ask, rather than the mechanics of how is this data structured, how do I need to ask this question to make this thing understand me. So the idea is that we're able, through OGC, sort of this OGC API lens, is we're able to craft consistent and agnostic, infrastructure agnostic queries that can then be directed in the back end of these servers down to the specifics. One of the things that we're sort of doing, and this is where we're heading in the OGC space is looking at, okay, so we can do this at DGS agnostic sort of interactions, but there are some really important and powerful DGS specific functions and sort of approaches. And the question that we're sort of I guess asking and resolving is what would that DGS specific API kind of look like? And I mean, the reason why there is a need for that is for certain use cases that actually want to drive the power of the DGS, of being able to do multi-resolutional and multi-source data integrations in the one hit, with that where everything is all nicely and consistently sort of traversable. They're the sort of things that you might want to actually really sort of dive in and do that. But again, there is an opportunity for us to do this in a way that is agnostic to the individual DGGS resource that's underneath, whether it's H3, RHELPix, or any other one. So long as it sort of is standards compliant DGGS, then all of those capabilities sort of will flow through without any major blockers. And so I'll briefly go through some of the recent sort of innovation projects that have been focusing on DGS APIs, and these have sort of kind of led us to where we are now. So I'll start off with some work that was done a couple of years ago by Barry Peterson and his team out of Pixis, sort of working sort of directly with Natural Resources Canada, looking at sort of building out web API interfaces to the Pixis or Global Grid Systems DGGS. Sort of, and some of the stuff that came out of that actually sort of got us thinking and moving into I guess this direction of a common and sort of generic DGGS query language that can work across all of those. And we started in testbeds, OGC testbed 16, which was sort of running last year in 2020. We started to dig into some of these things, but now with sort of the passage of a couple of years, we've looked into the emergence of OGC APIs and so, well, okay, so where does this concept of unified generic sort of language, query languages, how would that sort of look in the context of OGC APIs? And some work that I've been involved in sort of in parallel is looking, sort of drilling a little bit deeper into that around the use of or the development of modular OGC API workflows, where you can sort of string multiple OGC APIs together, including DGGS sort of enabled sort of services, but to be able to do it again in this consistent and in some cases completely DGGS agnostic way. And so that's some of the recent work, and all of these pieces of work have been very useful in helping us sort of plot the path to what an appropriate DGGS OGC API for DGGSs would look. So let's start with sort of just a quick overview of the Pixis DGS library. I'm aware that we're sort of running short on time. So essentially with what the Pixis sort of library did, NRCan what they wanted to do was to be able to do a distributed sort of multi-data hub sort of interface, and in order to do that, they needed to be able to sort of have this connectivity. And what Harry and his team sort of did is they took a good look at how the sort of their DGGS engine is structured and how it can be sort of rationalized into the different, I guess, topological groups of functions, from discovery to quantization, or and to geoprocessing or analytics. So just quickly, if we drive through this, so we can so in the discovery we can do things like searching, resolving, looking at different structures, where is it, what's here, those sort of questions, which is kind of the sort of standard way we've been thinking about using DGGSs. And then we've got quantization, so things like where you're converting data, or binning or mapping data from non-DGGS sort of context into a native DGGS context, and how that might look. And you've got things like looking at data details, data as cell values, and so on and so forth. And then we've got the geoprocessing, and this is where it starts to get kind of interesting, because if you think about a DGGS, I mean, is the way they're driven is a bunch of processes, but as opposed to discovery processes or just mapping or binning processes, when you start getting into the geoprocessing, you can sort of start to get into some really interesting places where you're doing iterations and calculations of and aggregations of data to solve a problem. And that's really, I mean, as a geophysicist, that's the sort of stuff that really excites me with those capabilities. And again, with careful sort of structuring of your server infrastructure, you can piece this together in a way where you can create these rather complex workflows, but using simple and consistent building blocks. And while the sort of this early work was not strictly OGC API sort of compliant one, it was just like before that time. But a lot of the thinking and the reasoning that came out of this project has really helped guide sort of our thinking, particularly around the concept of a DGGS agnostic and unified or general query and processing language. And then we moved on to testbed 16. There was a whole raft of things that we did, and I won't sort of labor on these. Some of this we've actually seen in previous coffee talks and other presentations. But we delved into things like a DGGS-centric well-known text, a spatial temporal sort of query language, what do topological functions in the DGGS context look like? And then it's sort of part of testbed 16 was sort of demonstrating and sort of implementing, and there was two sort of client server implementations tested, and those were focusing on different OGC APIs. One was focused on the processes, and the other was focusing more on the features. And they both demonstrated that multiple DGGSs, in the case of testbed 16, we used H3 and our heel picks, were able to equally sort of be represented and driven even via standardized non-DGGS centric process APIs or feature APIs. So which is really impressive. I won't stress too much on this, lots of text on the page, but essentially the well-known text type was we're sort of looking at, well, there is a concept of well-known text for sort of regular sort of spatial and sort of CRS applications. Well, what would that look like if we sort of thought about what the equivalent object in a DGGS would be? And so we have things like a point being or a multi-point essentially being an order ordinate list of DGS cell centroids, for example, as an example of that. Or if we've got a list or a collection of points, that could sort of be a list of cells. Or if we're looking at tile sets or job queues, well, you could have this sort of tile sort of matrixy type structure that's driven from the DGS perspective. And yeah, so I won't go too much on that, but feel free to drill into both this presentation and the testbed 16 report, which goes into quite a lot of detail on this. So when we're looking at spatiotemporal, it gets interesting here, but the advances that we made with the OGC standard, so topic 21 for discrete global grid systems, is that the core data model now can handle spatial and temporal descriptions of DGS resources. And so in testbed 16, we were sort of trying to unpick, well, what would a common language that worked across not just spatial but also temporal, and the interesting and sometimes complex ways that that works. But we've got things like boundaries and buffers and disjoints and overlaps and child and parent sibling sort of relationships, as well as relative position and sort of relate positions, which are concepts that work equally in spatial and temporal contexts. Yeah, and so we've sort of we drilled into sort of trying to pick out and articulate, well, how do we, is there a way for us to be able to do both temporal and spatial at the same time? Because often what happens is we do spatial and then we sort of time just is relegated to just a data parameter. It's not actually dealt with as an intrinsic part of the location of an object, and this gives us an idea of where to go. And like what Kevin showed in his presentation as well, and we've shown previously as well, when the DGS are quite a powerful infrastructure, and one of the things that's most powerful about them is that topological relations, which means that we can do things like the sort of spatial querying and the sort of reasoning. We can do hierarchical traversals. All of these things we can do that are sort of innate and intrinsic within the DGS sort of infrastructure. And then as part of testbed 16, we then drilled into well, we've got to have some implementations on the ground. And here's an example of the sort of the Swagger or the open API sort of interface that's describing and sort of how these things sort of hook together. And this example is from the processes API. And as you can see down here on here, we've got the core sort of common sort of requirements for this API server, having collections and conformance and landing pages, whatnot. And then we get down into the DGS specific things where we're describing particular DGS, we're describing the zones or cells of a DGS, and we can start to get into processes of, well, give me the neighbors. Well, that itself is a process of finding the neighbors, but it can be accessed by a consistent methodology. And I guess to get some pretty pictures, what was shown was that it was actually quite simple to be able to do some of these sort of conventional spatial analytics in the context of a DGS, but driven through a conventional OGC API for processors. And this is implemented in GS Server, and not only for one DGGS, but for multiple multiple DGGSs. So it's a testament to both the power of the of where the OGC APIs are heading, but also the standardization across different DGGS instances. And then sort of in parallel to that, and sort of more, I guess, slightly more recently, because the project has continued on. Some of the work that I've been doing in the modular OGC API workflow space is, I guess, takes this concept sort of even further. Where before we were talking about, well, an OGC API server or resource. The workflow concept enables us to daisy chain multiple servers together, and so essentially your workflow involves a process usually, whether it's simple or more complex, and a set of inputs, and those inputs could be individual API resources or servers. And if we unpick those, we actually see that, well, they could be a DGGS or tile collection. They could be feature collection. They could be a coverage collection. They could even be query or static or dynamic function parameters. And actually, what's really cool about what came out of this project is that we can have nested workflows and processes within a workflow, and they all work really nicely. The concept of it is that when you validate a workflow, you'll follow that daisy chain all the way and make sure that, yep, I can see this resource, I know this resource has got data, and it's ready to go. And then you can fire off a query to that workflow, which then will direct the relevant parts of that query to the relevant service inputs, which then sort of come back and give a consistent result. Oops. And so so my sort of DGS, multi-DGS platform, Terra Nexus, was used as part of the guinea pig for doing this and exploring sort of how to piece together these workflows, but also to be able to demonstrate that you can do this with a DGGS engine under the hood, sort of as operating as one of these processes that works on data, but the actual query or workflow that drives that process does not have to know anything about your DGGS at the back end, and that was pretty cool. And so if we sort of pick apart one of these sort of workflow execution documents, if you want, we've got the process sort of resource. So this is where that resource lives, and in the back end in the server, a sort of set of processes are driven from that endpoint. Now that process is expecting a number of inputs. This particular one is looking for primarily two different classes of input, but also within that they can be nested, they can be arrays, they can be single values. So there's a whole range of flavors that can be done there, and we're not bound by they must be static sort of web service type or API resources, as you can see here with sort of these roads or buildings or contours. They can actually be another workflow and another process. And whereas this one here is actually a process that takes a DEM image and converts that to a set of polygons. So this kind of leads us all of these different projects focusing on different things. This leads us to sort of the next steps of where we are, and that's kind of where we are in the OGC DGS standards working group. And now we're looking at sort of the way forward, and how do we craft a set of or hopefully one, but maybe one or a set of specifications that adequately describe the functions to drive a DGS, a generic DGS API that can help bring together and drive data integration, not just within particular DGS, but across DGS instances. And that's all I have. So, any questions?
Great. Thanks, Matt. I'm not seeing any questions in the chat at the moment. So remind participants that if you want to ask a question, you can type it in the chat. But also, I guess we can take questions directly if you want to just raise your hand. I'm not seeing any hands raised at the moment. So I have a question going back to Kevin's presentation. And Kevin mentioned briefly something called Project Fairhair, which was a project that the GFGS was involved in a couple of years ago. We actually checked, and there's pretty minimal information about this on the wiki at the moment, so we're going to rectify that and put some more there, because it was really quite interesting work. But I wonder, Kevin, would you be able to just say a few more words about what was being done in that project and the sort of outcomes that we saw? Thank you.
Sure. I mean, so my role in it was just generating grids for various countries with DGGrid, but the idea was we had 15 different countries that we generated grids for, all the same resolution, and the individual members of the GFGS took those grids and they binned population data into it, and then they tried to do a comparison of sort of the accuracy and efficiency of binning into a hexagon grid versus a square grid. And the Inspire grid was the one that was sort of motivated versus the hexagon grid. And there's also some discussion of privacy issues that took place as a result of that. And as Steve pointed out, I didn't have the PowerPoint. I didn't have a link to the PowerPoint to put into my presentation, but that should be up hopefully shortly. And the idea there was just really to prove that you don't need a dedicated tool in order to use a discrete global grid system. The existing workflows are powerful enough to handle large volumes of polygons. So if you get a bunch of polygonal cells, you can just treat them as polygons and use the same sort of workflow you would use with any set of arbitrary polygons to bin data into it and to visualize and so on. And within 2 weeks of my generation of the grid, there was the presentation. 15 different countries all were able to successfully bin with no difficulties whatsoever, using different production workflows depending on the individual researcher. They were all successfully binned their population data and visualized it and did some basic analysis with it in 2 weeks. So it was really a demonstration to show that you don't have to wait for tools to come out that make it simple to work with a discrete global grid. You can just use your existing workflow and just treat the cells as just arbitrary polygons. And computers, I was actually personally very surprised, because I've always been sort of, my interest is in working on such tools, and I've always been looking at that in the future. And it was really Vilny, the head of the GFGS, that pointed out that no, GIS tools are powerful enough now to even use on a global scale. You can even take fairly fine resolution grids and work with them in existing workflows. You don't need special tools. It's just polygons. And that was really, from my perspective, the important takeaway from Project Fair here. So I'm hoping we'll get the PowerPoint up there, and I encourage people to look at that and see exactly what Vilny and the other GFGS members did.
Great. Thanks, Kevin. Thanks. So I'm still not seeing any questions, maybe if anybody had trouble finding the chat or the raise hand function, then feel free to just jump in with a question. So in the meantime, just maybe, Matt, if I could just ask you to say a few words in general about the OGC, because I'm not sure it will be familiar to all of the participants. So just like a sort of 30 seconds OGC in a nutshell, what it is, how to get involved in the activities and so on. Thank you.
Yep. So the OGC is an international member-driven consortium. It's a standards development organization, specifically focusing on building geospatial standards, particularly to sort of enable data integration and interoperability. They've got a wide range of members, from small sort of startup companies right through to the big players of Esri and Google and Apple, and even Microsoft are now our members, and through to government and research organizations. So they pretty much cover sort of the three main sort of industry sectors: research, private, and government. Multiple sizes, nearly full global coverage. But the idea is that everybody comes together and sort of pools their intellect and resources to drive open and standardized ways to deal with data.
Great, thanks. And if anybody wants to find out more, you can do what I did a little while ago and just Google OGC. And actually, it's a really wide range of activities there that may be of interest. Okay, so it's the absolute last chance for any questions or comments, because we've reached or just gone very slightly over the end of our hour. Again, I'm not seeing anything, so I think everything was very clear. I would like to thank again our two presenters today, particularly because they were both joining us at what most people would consider to be well outside normal working hours. So thank you very much for your flexibility to join us at this time. So with these Coffee Talk webinars, we're putting together the next one at the moment, which will be on standards for bringing together geospatial and statistical information, looking at the global statistical geospatial framework and something called the geospatial GSBPM. So that's just a taster of what's coming up next. That will be in about 3 weeks' time, but the information will be circulated in the next week or so. Also, just to mention, if anybody's interested, I was talking to somebody yesterday and they came up with the idea of having one of these coffee talks looking specifically at visualizations and what's new and trendy and really interesting in visualizations, looking at data through a geospatial lens. So we're thinking about putting together something maybe with some short, like 5-minute presentation demonstrations sometime later on this year. So if anybody's interested in that, just drop me a line and I'll keep you in mind for when we put that one together. So I'm seeing we have in the chat, we have a question that's appeared. So the question from Gopa, we'll just take this one briefly before we close. DGGS is transparent to the users, except for improved data integration and performances. Will there be an elaboration? So I don't know, whether Kevin or Matt, you want to comment on this?
Just trying to sort of get what they're really asking. Are they asking?
Yeah, maybe the best
are they
is
asking sort of about the, I guess, the metrics of data interoperability or integration, or yeah, I'm not quite sure, because I think both Kevin and I sort of discussed, and Kevin showed some really good examples of improvements to interoperability through the use of DGGS. I'm not quite sure if what the question is really targeting.
Yeah, so Gopa, does that answer your question, or would you like to just take the floor? You can unmute yourself and ask your question if you wanted to look at a different angle.
Thank you for giving me the opportunity. Really, I was involved with this water body sensors in India. Okay, they were taking pictures of the water bodies, and then that was translated into the data. So I was rather interested to have this, to listen to this talk. I think, yeah, for the time being, it's okay. In case something comes to my mind, I will definitely get back to you, because yes, short of time. And thank you very much for giving me the opportunity. Thank you. I was audible?
Yes,
Hello.
great. Yes, so thank you for that. And you're of course welcome to get back to us if you want to ask anything further.
Right. Will this be presentation shared? Like?
Yes, the two presentations will be on the GFGS wiki, which is what you went to register within the next hour or so. And the recording may take a little longer because these things take a while to upload, but everything will be there by tomorrow.
Okay, sir. Thank you very much. Thank you, sir. Namaskar.
Okay, thank you. So I think with that we can close. So thank you everybody for joining. Thank you again, the presenters, and I look forward to seeing you all at a future Coffee Talk webinar. So thank you and have a very good rest of the day.
Bye, sir.
Take care, everyone.
Bye.